Alright, so Go is a very interesting language, and by interesting I mean that when wielding this language you're given the opportunity to effortlessly spin off an army of concurrent functions with just a few lines of code. But as the old saying goes, with great power comes great responsibility. And that is to say that although syntactically firing off these little guys can seem effortless, the reality is that delusion can result in some very buggy and difficult to maintain code. So in this video, I'm going to try to quickly explain all of the necessary Go concurrency patterns that you can use to write performant and maintainable code. And in this video, we're not going to get into too much of the theory behind concurrency. That's something that I'm kind of going in this expecting you to understand. This video is going to be a more hands-on approach to learning concurrency patterns in Go. We're going to start with the primitives that are used to actually write concurrent code in Go. And from there, we're going to build concurrency patterns using those primitives that we learn. And with that in mind, let's just go ahead and jump in and get into Go's concurrency primitives. And there are three that you're going to need to understand and be able to wield to make use of these patterns. They are goroutines, channels, and select. So we're going to start with goroutines. So what is a goroutine? Okay, so we're just going to start here by creating the main function to our program. So we'll just do func main, and this is going to be the entry point to our program. So when our program is run, this function is what's going to be run. And within this function, we're just going to do format print line, and we'll just print hi. And we'll just save that and go into our terminal and run the program. And as you can see, we get hi printed to the screen. So aside from our main function, we can also create another function, and we'll just call it sumfunc. And this function is going to take in a number as a string, and this function will just print that number. And in order to run this function, we can call it from within our main function, because remember, the main function is the entry point to our program. So we can just do sumfunc, and we can pass in a number as a string. And actually, let's just go ahead and do 1. And we can save that, and we can run it. And as you can see, we get 1 printed, and then we get hi printed to our terminal. So here, when we're calling this function from within main, this function is being run synchronously. And that means that our main function is going to be blocked until the completion of this function. So this format print line here won't run until after sumfunc is finished running. But with goroutines, we can actually make sumfunc fork off of our main function asynchronously. And that would mean that main would not need to wait for sumfunc to finish before it could continue with its work, which in this case would be to go and print hi. And we do that simply by just putting the go keyword in front of the function call. So this here is a goroutine. So when we run the program, main's going to run, and it's going to fork this function off of its own process, which essentially means that this function is going to be spawned, and it's just going to go and run, and main's going to go back to what it was doing. It's not going to wait for this function. And that gives us the power to run functions concurrently, because we could do multiple of these, and main would just go fork this off, and then fork this last one off, and go and continue with what it's doing. So for example, if we save this and we go into our terminal and we run the program again, you see that hi gets printed, but the results of sumfunc, the above 3 calls to sumfunc don't get printed. And that's because mains, basically, these processes are just forking off of main, and they're going to run, or they're going off to do whatever work is defined within the function. And once main just sends those off to do what they need to do, main's going to go back to what it was doing. It's not going to wait for them. It's not synchronous. It's asynchronous. So we're asynchronously calling these functions. So with that in mind, how do we actually see the results to these functions? Because they're in no way synced with main. Like they never rejoin main, like we can't see the results for them, right? So let's just go ahead and change this to 2 and change this to 3. We can actually just do time.sleep and we'll just do time.second times 2. And this is going to make main wait for 2 seconds once it gets to this line before going to perform this code here. And 2 seconds should be enough for these 3 goroutines to finish running. So if we save this and we go back into our terminal and do go run primitives, you can see that in no particular order we get the 3 numbers printed to our screen. And the reason that they're not in any particular order is because, remember, these are just asynchronous, they're not synchronous. So this one doesn't wait for the completion of this one. It's like basically whoever prints first is what gets printed to the screen first, because they're all running concurrently, right? So these are goroutines. And this is one of the most essential building blocks to concurrency in Go. So let's briefly go over how concurrency in Go is structured. You'll recall that our main function is the entry point to our program. It's essentially the parent function to any other function called within the program. And you'll also recall that these goroutines fork off of the main function. So what does that actually mean? Well, let's have a look at a diagram. So Go follows a model of concurrency called the fork join model, which can be visualized using this diagram. So this diagram represents the life cycle of our main function. So here would be the start of our main function. And here would be the end of our main function. So the main function starts here and ends here. And of course, this main function represents this. And actually, we can just say this is the start and this is the end of the main function. So child processes or goroutines are forked off of the main function. The main function will fork a child process off of it, and it will continue to run just like we explained here. So this fork child here is actually representative of one of these goroutines being forked off of the main function. But with this fork join model, we see that our child process is forked off of the main function, but we also see that at some point that child rejoins the main function. And this point is called the join point. And actually, we're responsible for implementing the rejoining of the child process to the main process. For example, as you saw before, when we didn't have this time.sleep line of code here, we actually were never able to see the results of these goroutines because main basically just shot these off and forgot about them, and then it went and finished its own process, and we never got the results from this. And just so that there's no confusion, this time.sleep actually isn't representative of the type of code that is necessary to create a point at which the child can rejoin the main process or the join point. Because this time.sleep doesn't actually sync our main process with these concurrent goroutines. For example, if we were to sleep for maybe 100 milliseconds, maybe these still wouldn't have time to finish. That is to say that with our current code, our main function doesn't coordinate in any way with these goroutines, which means that our main function is technically not synced with these goroutines. So we technically don't necessarily have a join point yet, but we'll be responsible for implementing that later on down the line when we get further into the explanation. Okay, so now that we've gotten goroutines out of the way, let's move into our next primitive, which is channels. But before we get into channels, I feel that it's imperative that I inform you that it's in your best interest to like and subscribe to this channel. I know that that's a very bold statement to make, but I don't think that you'll be disappointed. And if you are, you can just unsubscribe. But anyways, let's get into channels. So what are channels? So channels are typically used to communicate information between goroutines. Because remember, our goroutines are running independently of one another and don't require knowledge of each other. So in order for our goroutines to communicate, we can have them reference the same place in memory, which is where a channel would reside. For example, let's say we have some goroutines and they're running along doing their thing. And let's say that goroutine 3 needs to communicate with goroutine 2. It needs to send data to goroutine 2. In that case, we could have a channel here that goroutine 2 will read from and goroutine 3 will write to. And we can really just think of channels as first in, first out queues. So let's say that the data that's being communicated to channel 2 from channel 3 are hearts. So 3 units of data are put onto the channel by goroutine 3. Goroutine 2 would just read off those units of data in, first out order. So this one would get read off first, and this one second, and then this one third. And remember, our main function is a goroutine as well. So that means that our main goroutine can communicate with its child goroutines through channels as well. For example, if we had another channel that our main function reads from and all of the child goroutines write to, in this way you can kind of see how we will be able to implement the before mentioned join point from the explanation of the fork join model. So how do we actually initialize and make use of these channels? Well, it's quite simple really. So if we want to initialize a channel, we can just do something like my channel equal to the result of the make function, and we're going to use channel, and we want the data that's passed through this channel to be of type string. And now we have our channel. So at this point we could make a goroutine, and we can just use an anonymous function here. So this goroutine is going to send data to the channel. So we'll do an arrow pointing to the channel, and next to that we'll put the data that it's sending onto the channel. And since this is an anonymous function or a nameless function, we need to invoke it now. So this is the syntax to send data to a channel. And from there we can have our main function read from the channel. So we'll just call the result message, and the main function is going to take in the data from my channel. So the main function is reading the data from my channel. And after that we can just print out the message, which should be data. And let's go ahead and save that, and just go ahead and open up our terminal and go run primitives.go. And as you can see, our main goroutine actually waits for the message. And that's because this line of code here is actually blocking. That is to say that the main function will actually wait for either this channel to close or for a message to be received from this channel. So you'll recall that during the previous explanation of the fork join model, we mentioned that we need to implement the join point, or the point at which the forked goroutine rejoins the main goroutine. And when writing this code, we actually implemented that. So if you have a look at the code within our goroutine function here, we see that we're putting this data onto our channel. This arrow means we're putting the data onto the channel. And remember, both our main goroutine or our main function and this goroutine or this function communicate via this channel that we created. So the goroutine is putting the data onto the channel via this arrow, and our main function is reading the data from the channel. So this is the channel, the data is going from the channel to this message variable. So at this point, both our main goroutine and this goroutine that is spawned by main, which would fork off and go do something here, is rejoining our main goroutine via this shared channel. So both our main goroutine and this goroutine are synced at this point. Because this line of code here is a blocking line of code, this means that our main function is actually going to wait for the data to be put onto this channel to receive it here. And then at that point, that's when we print this message that we receive from the channel. So at this point, we have a very simple example of a join point or a join point implementation. So that and the syntax for putting data onto the channel and to receive data from the channel are important things to note here. Okay, so now that we've gotten channels out of the way, we can move into the last primitive, which is the select statement. At this point, you should be starting to understand how all of these are going to come together to help us to form the patterns. But yeah, what is the select statement? So looking back at the code that we wrote for our channel example, we can just add the implementation of the select statement. So essentially what a select statement does is it lets a goroutine wait on multiple communication operations. And in this case, we can say that it's going to let our main function wait on messages from multiple channels. So let's go ahead and create another channel, and we'll just change the name of this channel to another channel. And this channel, like the previous channel, will be a channel that has strings as its values. And we'll go ahead and create another goroutine. So let's just copy that one. And this goroutine is going to put data onto another channel as opposed to my channel like this goroutine above. And we'll just change the data here. And now down here is where we're going to want to do our select statement. So currently we're only receiving data from my channel. So we can just delete that and delete that print statement as well. And we'll just type in select. And this is our select statement. And we're going to have case message from my channel. And this case will be for messages that come from the my channel channel. So my channel. And if that is the case, we're going to print message from my channel. And we'll have one more case here. And this case is going to be message from another channel. And this is going to be receiving messages from another channel. And in that case, we're going to print message from another channel. And that is our select statement. So a select statement is going to block until one of its cases can run. So in this select statement, we have two cases, but we could also have more, for example. But in this example, we're only going to have two. So the first case is if it receives a message from my channel, and the second case is if it receives a message from another channel. And it's going to block until it receives a message from one of these channels. And once it receives a message from a channel, it's going to execute the code within that block. If the select is able to receive messages from multiple channels at the same time, it's actually going to choose one at random. So if multiple messages are ready, it'll choose one at random. And that's basically it. That's what the select statement does. So now that we know what the select statement does, we can go ahead and open up our terminal and test it out. So we'll just do go run primitives.go. And you'll see that we get one of the messages, the message that goes on to the channel named another channel. But remember that if both channels have messages ready at the same time, one is chosen at random. And of course, if that's not the case, then one is ready before the other. So if we run this a couple of times, we should be able to get the other message as well at some point. And there it is there. And that is the select primitive. Okay, so we're finally here, and if you've made it this far, congratulations. We're now going to get into using the concurrency primitives that we learned to build concurrency patterns. And we're going to go over 3 patterns that I think are essential to writing concurrent code in Go, and you can actually build upon your understanding of these patterns to learn other concurrency patterns, because of course there are more concurrency patterns out there, and there's a good chance that there will be more to come. And with that being said, there's actually a really good book on concurrency in Go that deep dives into other concurrency patterns that I will link in the description. And let's just get started with those 3 concurrency patterns that I think are essential. So the first one is going to be the for select loop. So that's the one that we're going to start with. And after the for select loop, we're going to move into the done channel. And once we've gained an understanding of the done channel, we're going to move into understanding pipelines. So let's get started with the for select loop. Okay, so let's imagine a scenario where we have an array of characters that we want to put onto a channel. So we want to put each individual character onto this channel here. This is a simple example of where we would use a for select loop. And a for select loop is essentially just using a select statement for each iteration of a for loop. For example, if we were looping over the character array, or actually slice, and you'll have to excuse me, I'll probably make the mistake of calling a slice an array, but it's just because Go's not the only programming language that I work with. But anyways, let's imagine a scenario where we're iterating over this slice, and for each iteration we're using the select statement within the loop. So as demonstrated here, for each character in this character array, we're going to use a select statement here, and we're basically just going to put the character on the channel. And it's really as simple as that. For each iteration, we're just going to put the character on the channel, and we'll end up with this channel containing these characters. Okay, so let's have a look at what that looks like in code. So we'll start by creating a buffered channel, and by buffered I mean that this channel is going to have a limited capacity of 3, and we actually won't need a corresponding receiver for these 3 values, which is in contrast to the default unbuffered channel, which is essentially used to perform synchronous communication between goroutines. So in the past examples, we were using unbuffered channels. So the default, if we were to not put a capacity here, would be an unbuffered channel. For example, if we go to the documentation for make and we go to the documentation for channel, we see that the channel's buffer is initialized with the specified buffer capacity, which is the capacity that we're specifying when we're creating our buffered channel in the most recent example. And it also says if 0 or the size is omitted, which we were doing in the past examples when making channels, the channel is unbuffered. So in order for us to make communication between goroutines asynchronous, we need to actually use a buffered channel. So we're going to set the capacity to 3. And you might be wondering why the unbuffered channel resulted in synchronous communication between goroutines as opposed to asynchronous, and that's because an unbuffered channel provides a guarantee that an exchange between 2 goroutines is performed at the instant the send and receive takes place. But with a buffered channel, we're actually using the queue-like functionality, where we basically can send data onto the channel and just forget about it. So that means that the sending goroutine can just send and forget up to the allotted capacity, of course. So let's imagine that we created an unbuffered channel by not passing a capacity as a parameter when we created the channel using make. And let's also imagine that we have a sending goroutine that wants to send some data onto this unbuffered channel. When this goroutine sends the data onto the channel, this goroutine will go into a waiting state. So that means that this goroutine will be blocked, and it will be blocked until there's a receiver receiving the data from this unbuffered channel. Now let's imagine that we have a line of code for a receiving goroutine to receive the data from this channel. Once we reach this line of code and this receiving goroutine receives the data that was sent by this sending goroutine, at that point, this goroutine will no longer be blocked. And that's what I mean when I say that an unbuffered channel only allows goroutines to communicate synchronously. Because synchronous communication is when the sender needs to await the response from the receiver. So the sender is blocked until there's a response from the receiver. And in this case, the response comes through the channel. So you can think of it as the channel informing the sender that the receiver has received the data, and that's what allows the sending goroutine to leave that waiting state. Now with a buffered channel, we're passing in a capacity. So in this case, we're creating this channel, my channel, with a capacity of 3. In this case, communication between goroutines is asynchronous. So let's imagine that we have a goroutine here, and this goroutine is a sending goroutine. And once again, we'll send some data onto the channel. With a buffered channel, this goroutine isn't blocked. It will send the data onto the channel, and that data essentially will just get queued, and this goroutine can just continue with what it was doing. But that's only if we haven't yet reached the capacity. So if this channel were actually full, if it were actually at capacity, and this sending goroutine tried to put more data onto the channel, at that point this goroutine would block until data is read from this channel. But up until the capacity, the sending goroutine can put data onto this channel and continue with what it was doing. And if you notice, this goroutine is able to continue with what it was doing, and we don't even yet have a receiving goroutine. But this goroutine doesn't need to worry about that because the communication between goroutines with a buffered channel is asynchronous. That means the sending goroutine can just send and forget. So we can imagine that we have a receiving goroutine, and of course this goroutine can receive the data, but this goroutine isn't blocked in the first place. So the communication between this sending goroutine and this receiving goroutine is asynchronous. So we'll also create a slice of chars, and it'll be string, and we'll just put ABC. And all we're going to do is loop over that slice of characters, and for each character we're going to put it onto our char channel. And we're going to do that using the select statement, and we'll just do case char channel. And after we iterate over all of the characters in our slice and put them on the channel, we'll go ahead and close our channel. And at that point, we'd be able to loop over the result. So we can just say result equals, and we'll just print the result. And this code here actually tells us something. This tells us that we are actually able to loop over a closed channel and still receive the residual data that was put onto the channel. Because here we're closing the channel, and then here we're looping over the data that's in the channel. And this loop will end because internally it knows that the channel was closed at a certain point. So if we go ahead and save this and open up our terminal and do go run primitives.go, you see that we get ABC printed from our channel. And you're probably wondering why even use this select statement here. So for example, why not just do char channel and then just put the data on like that? And that's actually a good question, and we're actually going to get into that when we get into the next pattern, so just bear with me for now and know that we will get back to that later. So now let's go ahead and get into another example of our for select loop pattern. So let's suppose that we had a goroutine that we want to run indefinitely, or at least until its parent goroutine tells it to stop. So if we do go func and we just do for, and for is just going to be an infinite loop, and then we do select, we can use this default to just do some work. And here we have an example of an infinite looping goroutine. So if we just do time.sleep here, and we do time.second and save and go ahead and run this, you'll see that it's just going to infinitely print do work, well, at least until 10 seconds is up, because the parent goroutine, which is the main function, is actually going to just cut off after 10 seconds. But this is an example of the for select pattern being used to have an infinitely running goroutine. But you're probably wondering how this is even useful. Like, there's no way for us to stop it or anything like that. And that's when the done channel comes into the picture, which is our next pattern. So let's go ahead and get into the done channel. Okay, so in order to understand the done channel, we should understand what a goroutine leak is. Now, of course, there may be a case where you want a goroutine to run for the lifetime of the application, but what we want to prevent is unintentionally leaving goroutines running for the lifetime of the application. And in order to put that into perspective, let's imagine that this application is actually a production long-lived application. So if you imagine a real-world application with actual users, you don't imagine an application that only runs for 10 seconds. So to emulate this type of long-lived application, we can just change this to hour, and we'll just put some arbitrary number of hours there. And after, we could just go ahead and save, and then go into our terminal and go run. And you'll see that our infinitely running goroutine is doing work, right? But let's say, for example, we have a goroutine running that we don't want to run for the lifetime of the application. And we don't actually realize that that goroutine is running in the background and consuming memory and processing power and resources. That is an example of a goroutine leak. And that's something that we want to avoid when we're actually writing our code. And one way that we can deal with that is by implementing some sort of mechanism that will allow the parent goroutine to cancel its children. And that's where the done channel can help us in this situation. So let's go ahead and cancel that. So let's say, for example, that we want our main goroutine or our main function to cancel our infinitely running goroutine after a couple of seconds. So in this case, we could just create a channel that we'll call done, and we'll just do make channel, and it'll be a bool. And in this go func, we can just pass in the done channel as a read-only channel. And the way that we do that is we just use the receive arrow and channel as the type. And then of course we need the data type for the channel. And let's go ahead and just change this to do work. And we'll change this to func. And we'll remove that. And let's go ahead and cut this and put it outside of our main function. So now we have this do work function that's going to be a goroutine, and we'll just do go do work, and we're going to pass in the done channel. Now if we go back to the definition for our do work function, now we can make use of this done channel. And that's where the reasoning behind this select in our for select pattern comes in. Because we want our goroutine to do work by default, but if the parent cancels this goroutine, we want that to be a case as well. And what I mean by that is we can just do case, and if we've received from the done channel, we can just return. So that means that by default, this goroutine will continue to do whatever work that it needs to do, and the parent goroutine will have the power to stop this goroutine from doing work when it deems necessary. So if we go back down here, our parent can say that it wants this goroutine to continue to do work for, let's say, 3 seconds. And then after that, all the parent goroutine has to do is close the done channel. And when this done channel gets closed, this do work function will receive a case done. It'll receive a message essentially from the done channel, which will cause this do work function to return and stop the goroutine. So let's go ahead and try that out. And as you can see, after 3 seconds, the parent goroutine canceled the child's goroutine from doing work by using the done channel, by canceling the done channel. And a couple of things to note here. We're passing this done channel to this do work function as a read-only channel. And that's what this syntax is doing here. So this do work function can't actually write to this channel. It can only read from it. But as you can see, if we were to remove this select, we wouldn't be able to have this case where we check the done channel to see if the parent wants us to cancel this goroutine. And that's one of the reasons why the for select pattern is so common. But yeah, that is going to be the done channel. Okay, so we have finally arrived, and dare I say that this is the moment of truth. This is the moment that we learn the final concurrency pattern in this concurrency pattern video, the pipeline. So if you made it this far, congratulations, and yeah, saddle up and get ready for takeoff. Okay, so let's start by first going over what a pipeline actually is, just in a general sense. A pipeline is nothing more than a series of things that take in data, perform an operation on that data, and pass it back out. So the data goes into this thing here, does an operation on it, and passes the data back out. And that data then gets passed into this thing here, does an operation on the data, and passes the data back out. And we call each of these things a stage in the pipeline. And all of these stages working together form the pipeline. And by using pipelines, we can separate the concerns of each stage. For example, say that the data that we pass into the pipeline is a slice of integers. And let's imagine that we want to do something random with each value in this slice, like we want to square each value in this slice, and we want to convert each resulting value to a string. Instead of having one stage that does all of that, we can separate the concerns, which in turn will make our code more modular and more organized. So we can have one stage to actually square the number, and we can have another stage to convert to string. And in this way, we can modify stages independent of one another. We can mix and match how the stages are combined, independent of modifying the stages, etc. So separating the concerns is just something that's beneficial overall. So now that we understand what a pipeline is in a general sense, let's get into understanding how that applies to our concurrency patterns. So the start and the end of our pipeline is going to be orchestrated via our main function like so. So if we have an input here, and we'll just call the input nums, that input is going to be passed to the first stage of our pipeline. So we'll do stage 1, and the output for stage 1 is going to be a channel, and we'll call it data channel, and we'll set it equal to the function that will be responsible for the logic for that particular stage. So the first stage, we're going to convert this nums slice into a channel, or we're going to put each element from this nums slice onto a channel. And the resulting data is going to be this data channel. So we'll call it slice to channel, and we're just going to pass in nums as the value. So we'll create that in just a second, but now we'll move on to stage 2. And for stage 2, we want to pass the output from stage 1 into another stage. So this SQ function is going to be the stage that squares each number from the original nums slice. And this stage is also going to output a channel. So we'll just call this one final channel. And again, we still need to create this function. And last but not least, for stage 3, we need to output the result of the entire pipeline. So main is actually just going to be responsible for stage 3. So we'll just do for n equals range final channel format.println n. So this is going to print the data that's been processed. This nums array is processed by going through these channels, and then we're going to print it here. So now we can go and create our actual stage code. So for stage 1, we're converting our slice of nums into a channel. So we'll just call this func slice to channel, and it's going to take in a slice of int, and it's going to return a read-only channel. And of course, we need to add int for that as well. And this stage, we're going to create a channel, and it's going to be an unbuffered channel. So keep that in mind. And then we'll just spawn a goroutine. And for each item in that slice, we'll add it to the out channel. So we'll do n equals range nums, and we'll put n onto the channel. And this is an anonymous function, so we need to invoke. And once the for loop is finished, we're going to close the out channel, and we'll return out. Now remember what we learned in the beginning of this video. This goroutine is asynchronous. So we're going to spawn this goroutine here, but slice to channel is not going to wait for the goroutine. It's just going to return the channel. And I'll explain that further in a little bit. So now we're going to create our square function, and it's going to take in a read-only channel, which we'll call in, and it's going to return a read-only channel as well. And here we'll also set an out channel, which will be int, and it's going to be an unbuffered channel. And here we'll also spawn a goroutine. But for this function, we're going to range over the in channel, which is going to be the channel that is returned from the slice to channel function. And we'll write to our out channel the square value of each number from our in channel. And once this loop is done, we're also going to close the out channel. And then we will return out. So once again, please keep in mind that this go func isn't going to block the rest of this function. We're going to send off this go routine, and then we're just going to return out. And that means that potentially this go routine could still be sending values to the out channel, even at the time that we return it. So let's take a second to try to visualize what's happening here. Let's try to visualize our coded pipeline in a similar diagram to the original explanation of pipelines. So we're going to have a start and an end to our pipeline. And this here is going to be our input. And the pipeline will have stage 1, stage 2, and stage 3. And this will be our data. So in each stage, we're going to do something in particular, right? So this first stage, we're going to do this slice to channel. So we're going to convert this slice into a channel, and the resulting channel will be here. This outputted data will be outputted as a channel. So this is actually this, and this is actually this. And here at stage 3, we're actually printing out each individual piece of data. So this would actually be multiple individual pieces of data being printed out. So with this, you can clearly visualize how this is representative of a pipeline. But the difficult part to understand is the actual code within this slice to channel and within this square function. So here we have both our slice to channel and our square functions. And the returned channel from this function is what we're passing into our square function. And as mentioned before, this goroutine here doesn't block this slice to channel. In slice to channel, we're creating this out channel, we're shooting off this goroutine, and we're returning the channel. And then that channel gets passed into this square function. And at that point, we're creating a channel here as well, an out channel. Then we're firing off this goroutine, and then we're returning the out channel, which is later on printed by our main function. But all of this communication between these goroutines is happening synchronously, because remember, we're not using buffered channels, we're using unbuffered channels. So that means that this goroutine and this goroutine are communicating synchronously. And remember, an unbuffered channel has a capacity of 1. Like, we can't send more than 1 value to this unbuffered channel. So what's actually happening here? So we're firing off this goroutine, and then we're returning the channel. So I want you to imagine that both this goroutine and this goroutine are running at the same time, because that's technically what's happening here. So this goroutine is iterating over the input slice of nums. And when it puts one of these numbers onto the out channel, it actually blocks until that number is read from the out channel. So we return this channel while this goroutine is still running, and this function has that channel, and this goroutine is reading from that out channel from here. So for each iteration of this nums slice, this go function actually blocks until whatever value that got put on this out channel is read by this goroutine. So this goroutine is writing to this out channel. This goroutine is reading from that out channel here. So this goroutine puts a value onto the out channel and then blocks. And then this goroutine reads that value from the out channel and then it blocks until there's another value on this channel. And then this goroutine puts another value on the out channel and then it blocks. And then this goroutine reads another value from the out channel and then it blocks again. And this goroutine, you probably would imagine that since an unbuffered channel only has 1 value, we can't really range over it, but that's not the case. We can range over it just fine. So what's going to happen is whenever there's a value put onto this channel, since this channel can only have 1 value, we'll read off of it, and then this range will just wait until another value is put onto the channel. And it'll keep doing that until this channel is closed, which is why after we put all of the nums onto the channel, we close this one, because when we close it, this range here is going to receive that close, and it's going to know that this for loop can stop. And then once that happens, we know that we can close our channel here as well. So that's what's happening between these two functions, or these two stages in our pipeline. And the same thing is happening with this out channel. If we have a look at our main function, we see that this square function is outputting its out channel in the name final channel. And we see that stage 3 is ranging over final channel. So the same way that the square's range was able to range over an unbuffered channel, this range can also range over an unbuffered channel. And it's doing the exact same thing that we were doing inside of this function. It'll read off of the channel, and then it'll wait for another value to be put on this channel, and it'll do that until this channel is closed. And you saw that within this function, we closed this channel. So you can see how all three of these stages are synchronized, and we're processing each value and then printing it. So this entire slice will go through our pipeline and end up being printed. And when each individual value is printed, it will be printed as the square of its original value. And that is a relatively simple example of a pipeline. So now we can just go ahead and test to see if our pipeline is working. And as you can see, we get the squared value for each item in our original int slice. And you can also see that it's in order because the communication between our goroutines is synchronous.